We're going to discuss the electronic configurations of anions and cations. And you might remember an anion is a negative ion, and a cation is a positive ion. And let's just write the electronic configurations to start for, well, we'll do aluminum metal, and then we'll do aluminum 3+. So for aluminum metal, look at its position on the periodic table here, and you can see we're going to need to put in 13 electrons. So we're going to start here in the 1s, following the periodic table. We'll put 2 electrons in, one for hydrogen and one for helium. Then we'll drop down here to the 2s, put an electron in for lithium and beryllium, move across here to the 2p, 3 orbitals in the 2p subshell, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now we'll come down here to the 3s orbital. We're up in energy, of course, and then we have one for sodium and one for magnesium. And then we'll jump across to the 3p, and we'll put an electron in for aluminum. And so this would be the electronic configuration for an aluminum atom. To make the cation, we're going to need to remove 3 electrons in order to get this positive charge. And we're going to remove, well, the 3 valence electrons that exist in aluminum. And so for aluminum 3+, we would just write 1s2, 2s2, and 2p6. And you'll notice that 3 electrons have been removed, giving the aluminum ion a 3+ charge. Now let's write the electronic configuration for oxygen and the oxide ion. So oxide is going to be oxygen that has gained 2 electrons. So if we're going to write the electronic configuration for oxygen, we're going to have a 1s2, 2s2. How many are we going to need? 8. We're going to need 8 electrons total. I've got 4 in already. We're going to need the 2p. And so I'll put in, let's see, we've done hydrogen, helium, lithium, beryllium. Now we'll go across to here. Boron, carbon, nitrogen, oxygen. And this would be the electronic configuration for an oxygen atom. If I want to make the oxide ion, I have to put 2 electrons in. I have to add 2 electrons, and that's pretty easy to see where they're going to go here. They're just going to go in here to the 2p, and they're going to fill this 2p subshell. So we'll just do 1s2, 2s2, and then it's going to be 2p6. And look at that. When we're done, we find that the electronic configuration for the oxide ion is going to be the same as the electronic configuration for the aluminum ion. Well, then you might ask, well, what makes these different? Well, let's remember here. With aluminum, you're going to have a +13 nucleus pulling on these 10 electrons. So there's a +13 nucleus. And then over here with the oxide ion, we're only going to have a +8 nucleus pulling on these 10 electrons. So while we have the same electronic configuration, we have a different nuclear charge, and so we'd actually expect the aluminum ion, the aluminum 3+ ion, we'd expect that to be a little smaller because it can pull these electrons in more tightly to the nucleus, and we'd imagine that the oxide ion would be a little bit larger. Now I also want to show you how we find the electronic configurations of the transition element cations. So those are going to be, these elements that run through here. And we'll do iron. Let's run iron. and we'll do iron 2 plus, or the iron 2 ion, and we'll do the iron 3 ion. So we'll start up here with the iron atom. And so we'll start, of course, with 1s and put 2 electrons in. That gets us here. Now we're going to go to the 2s, and we'll put 2 electrons in to get us to 4 electrons. And then we jump over here to the 2p. We're going to put in 6 electrons in the 2p. And then we get here at the end of the 2p, we got to go here to the 3s, 1, 2, 3s. So now we've put in 12 electrons. I'm sitting here where magnesium's electronic configuration would be. Now I'm going to jump across to the 3p. The p subshell gets 3 orbitals into which 6 electrons can go. And when that 3p subshell is filled, I'm over here at argon. Then I'm going to move to the 1, 2, 3, 4s. And I'm going to put in an electron for potassium and calcium, so the 19th and the 20th. And now we're going to put in, this is the 3D. You might remember that whichever period you're in, if you're in the D region of the periodic table, you go 1 minus the period number. So here, I'm going to put in, for any D subshell, we're going to put in 5 orbitals. So this is the 3D. And to get to iron, I have to put in 1, 2, 3, 4, 5, 6 electrons. And we got to remember, we're going to line the spins up first in separate orbitals before we start pairing them up. So I put 5 in. So that put me at scandium, titanium, vanadium, chromium, manganese, and then 1 more for iron. And so this would be the electronic configuration for the iron atom. Now we're going to do iron 2 plus. Now, I'm not going to write this out all over again because we know how to do this. I'm going to use the noble gas shortcut. So I'm going to take all the core electrons and I'm going to bracket them in the nearest noble gas's electronic configuration. If we look at iron, the nearest previous noble gas, I should say, we go back here to argon, and that would be all the way through the 1, 2, 3p subshell filled. So I look up here at this, and I see all the way through the 3p subshell filled is here. And this is the electronic configuration for argon, and I can represent that just by putting an argon in brackets. And by sticking this argon in brackets, what I'm basically symbolizing is 1s2, 2s2, 2p6, 3s2, 3p6. All of this is encompassed by just sticking argon in brackets like this. Now, to make iron 2, I'm going to have to remove 2 electrons from this set. And what happens with the transition elements, although we fill the 4s prior to filling the 3d, when we get to the transition elements and we want to make the ions where we're removing electrons, we actually remove electrons from the 4s before we remove them from the 3d. So what I would have here is an empty 4s because I'm going to take these 2 electrons out, and then of course the 3d is just going to look the same because I didn't mess with those at all. So the 3d is going to look like this: 1, 2, 3, 4, 5, 6. And that would be your electronic configuration in the orbital box notation for the iron 2 ion. Now if we want to do iron 3, of course we're just going to write the nearest noble gas in brackets. That represents all these electrons here. And then I'll write my 4s just to kind of remind me that I've taken 2 out. And now I'm going to remove this electron here from the 3d, and that's going to give me a half-filled subshell. So we're going to go ahead and put in the 3d, my 5 orbitals that are in the 3d, and then this is the electron that I'm going to remove. So I'm going to put in 1, 2, 3, 4, 5. I've removed these 2 electrons and this 1 electron from the atom to make the iron 3 ion, and I see that I have all these electrons aligned because we remember this idea that nature kind of likes to have magnetism. It likes to have these electrons aligned, and we also get a half-filled subshell to boot.